Hello and welcome to the session 4 on semiconductor diodes. In this session, these are the objectives. We will learn voltage rectifiers. We'll try to see how we can make a half wave rectifier and a full wave rectifier. There are two types of full wave rectifiers. We will see the working of each of them, and we'll try to derive an equation for the efficiency and ripple factor of each of them. So what is a voltage rectifier? So here I have shown a diagram which is like a schematic diagram which tells you what is the job of this rectifier. The block that is shown at the center is the rectifier, and on the left side a sine wave is going into it, and but when it is coming out of it you can see the negative part of that sine wave has been removed. So that is the job of the rectifier. It makes the current flow only in one direction, or it is converting an AC voltage into a DC voltage. So we'll begin with half wave rectifier. This is the diagram of a half wave rectifier. I have shown the circuit diagram. You can see whatever is at the middle is the circuit diagram. On the left side you have got the input sine wave, and on the right side you have the DC output which is coming out of the rectifier. And the core portion of this rectifier is the diode D, and the diode is connected to a load resistance across which we can measure the output voltage. And the inputs to the voltage rectifier is the voltage appearing across the secondary of this transformer. So if you examine the left part of this diagram, you begin with a wave which is the inputs to the whole device, and this AC is going into the primary of a transformer, and it is making a step down process there. You can see the number of turns in the primary is more than the number of turns in the secondary, so essentially this is a step down transformer. And why we have to use it is because the line voltage which is coming to our building is typically 230 volts, and you cannot apply that directly to the diode. So to be safe, you will step down the voltage, and the lowered voltage is appearing across the secondary of the transformer, and that will be given as the inputs to the rectifier. Rectifier part is actually this diode and the load resistance. So you have used a transformer here. That is only one option of using giving the input voltage. You can, if you have got a low voltage AC source, then you can use it directly. But here transformer is a convenient way of giving a low AC signal to the rectifier circuit. So we have drawn the circuit using the transformer. Uh, so we will see how we can explain the working of this rectifier. Here the AC inputs that I have drawn here, we'll consider the top part to be the positive half cycles and the bottom part to be the negative half cycles. So during the positive half cycle, the polarity of the voltage appearing across the secondary is considered to be in such a way that it is secondary is actually a coil. So you are measuring the output from the secondary from between the two ends of that secondary windings. So, and that is taken to be in such a way that the top end will be positive and the bottom end will be negative. During the positive half cycle, the top end of the secondary winding will be positive and bottom end will be negative. And then what happens is that during the positive cycle, since the polarity is like this voltage appearing across the secondary can be considered to be the bias voltage applied to the diode. So during the positive cycle, what we have is The positive of the voltage source is connected to the P region of the diode, and it will make the diode forward biased, which means during the positive cycle the diode will conduct. So it is conducting a current which is equal to I, and it flows through the load resistance. And when that current is flowing through the load resistance, it will dissipate some voltage across the load resistance, and that is what is measured as the output from the rectifier. And that voltage is not a constant voltage. You can see even during the positive cycle the voltage actually starts from zero. If you examine the sine wave, then it grows to a maximum value and then it decreases to zero. So during that entire interval of time, the diode will remain forward biased, but since the input voltage is varying, correspondingly the current will also be varying in a similar manner, and therefore the voltage drop across the load resistance will also follow the same variation. So that's why we don't have a constant voltage at the output. We have got a voltage which is varying exactly like the input voltage, but the only thing is that the negative portions are removed. And why is it so? Is because during the negative half cycle, the polarity of the voltage appearing across the secondary is like this. The top end will be negative and the bottom end will be positive. During the negative cycle, the top end of the secondary will be positive and top end will be negative and bottom end will be positive. So that means negative of our voltage source is connected to the P region, which will make the diode reverse biased. And since it is reverse biased, it will act like an open switch and it will not conduct. So that means during the entire negative cycles, the diode will act as a reverse biased diode will be reverse biased, and it will act as a open switch, and therefore it will not conduct any current, and correspondingly the voltage that we will measure across the load resistance will remain zero. So that means some voltage will be present only during the positive cycle, and even during that time the voltage will be varying because the input is varying. So we have using the half wave rectifier, we have successfully made DC output voltage from AC voltage. But the problem is that it is a fluctuating DC. It is not a constant DC voltage that we have obtained, but it varies between a maximum value and zero. So that is referred to as pulsating DC. That means it varies between a maximum value and zero, but that variation is a rhythmic variation. It is like a wave, like periodic variation. So since the variation is like this, this is referred to as a ripple in the rectified outputs. That means the rectified output is DC, but it contains a ripple which is essentially like AC. So that's why we will later see we'll have to, even after rectification, it contains a fluctuation which is rhythmic, and it behaves like, it is similar to a wave, and therefore it is like having an AC component at the rectified output. So that is what we will later find out, how much is the ripple present in the rectified output. A ripple is the AC component present in the output. So ripple factor is the ratio between the AC component and the DC component in the rectified output. Now, in order to find out the ripple factor of the half wave rectifier, what we are going to do is we will first of all draw the rectified output. You can see all the positive cycles are appearing at the output, whereas the negative cycles have been removed. So you have a wave which is drawn like this: time or phase along the x-axis, and the current along y-axis. A similar variation can be seen, or similar picture can be drawn for the case of voltage also, but here for the derivation of ripple factor we will consider current. So you can see I have drawn along the x-axis, I have drawn a small black vertical line. So at that point, it is the end of the first wave. One wave is starting from zero, it goes to a maximum value which is represented as Im, which is the maximum possible current or the peak current. Then from then onwards the current is decreasing to zero value, and it remains zero until this black line which I have drawn vertically along the x-axis. So that marks one complete time period. So in the case of time, it can be labeled as capital T or time period, or the corresponding phase will be 2 pi. And then what we do is you have some current, non-zero current present in the output only from phase 0 to pi. Okay, from pi to 2 pi your current is 0. The non-zero current is from phase 0 to pi. From pi to 2 pi your current is 0. So that is a fact that we are going to use in order to find out the ripple factor. The ripple factor is defined as a ratio between the AC component and the DC component, or normally we will write it as VAC by VDC, and it can also be defined using this equation. Gamma is the symbol used for representing the ripple factor, and it is defined like this. It is equal to square root of Vrms by Vdc the whole square minus 1. Okay, either you can use voltage or current in this equation. So gamma is the same as Irms by Idc the whole square minus 1 the whole raised to half. That way also you can write down the equation for ripple factor. And Vrms or Irms is the root mean square value of voltage or current, and VDC or IDC will be the average voltage or average current. So this equation can be rewritten like this. If you write it in terms of IDC and IRMS, you can write the equation like this: ripple factor is equal to root of IRMS square minus IDC square divided by IDC. So first we will evaluate IDC, which is the average current. So we take one complete cycle in which the phase will vary from 0 to 2 pi. Then you sum up all the current that is available during that time, and then you divide it by 2 pi. That is how we find out the average current. So IDC is equal to 1 by 2 pi. Then in order to find out the total current, you are doing the integration, but the limit of the integration is from 0 to pi, because from pi to 2 pi your current is 0. So since it is varying like a sine wave, you can represent the current like this: Im sine omega t, where Im is the maximum possible current or peak current. Im is the peak current, omega t is the phase. Okay, so this is your equation for average current IDC equal to 1 by 2 pi integral 0 to pi Im sine omega t. And if you do this calculation, you integrate this and apply the limit 0 and pi, and you will be getting Im by pi. So IDC in the case of half wave rectifier is equal to Im by pi. And we are not going to evaluate IRMS. We will take it from the definition of IRMS for half wave rectifier. It is actually equal to Im by 2. The RMS value of current is equal to Im by 2, and the average current or IDC is equal to Im by pi. So both these values, IDC and IRMS, in the equation for gamma is expressed in terms of Im. So now it is very easy for us to evaluate the ripple factor. You just substitute these two values in the above equation for gamma. And this is what you're going to get. You substitute the value of pi like 3.14, and you use the value of 2, and then all the Ims will be getting cancelled, and you'll get the number to be 1.21, or the ripple factor is equal to 1.21. That is what you're going to get. But the ripple factor is actually the ratio of the AC and DC components present in the output of the rectifier. That means how much is the AC component present even after rectification. that is given by this number. And interestingly, you can see that it is 1.21, which means the AC component dominates over the DC component in the case of half-wave rectifier, and that is a major drawback of half-wave rectifier. Now, if you proceed to do the derivation for the efficiency of the half-wave rectifier, we'll start with the standard definition for efficiency. Efficiency is equal to like how much is the output that we are getting for a given input. That is efficiency. So that is defined in terms of the corresponding power. So efficiency is actually the output power divided by the input power, and the output power, since it is rectified, it will be the DC power, and the input power, since it is AC, which is given to the rectifier, it is the AC power. So efficiency is PDC divided by PAC. Okay, now we will just use this equation for power as I square R, and in the case of output power, there is a current IDC which is flowing through RL. So PDC is equal to IDC square into RL. Whereas the input power, if you remember the diagram, you have got the input which is taken from the secondary of the transformer, and it is flowing through the diode and also through the RL load resistance. So the input current is flowing both through the diode and the load resistance, or the total resistance for the input current will be the sum of the resistance of the diode and the load resistance. So when you evaluate PAC, you have to use this equation, that is equal to IAC square multiplied by sum of the two resistances RL and RF. You can put a bracket over here. After I square DC and I square AC, you put a bracket because this RL plus RF is the number that you have to find out, and then you'll have to multiply that with I square AC. So in this case also you can substitute for IDC as Im by pi and IAC as Im by 2, and you'll be getting, then you have to make an approximation here. RF is the forward diode resistance and it is very small compared to the load resistance. So if you just divide in this part RL divided by RL plus RF, if you divide the whole numerator and denominator with RL, you're going to get 1 divided by 1 plus RF by RL, and it is a small number. You can sometimes neglect, or you can even write down that equation in terms of this 1 divided by 1 plus RF by RL. And apart from that, if you substitute for IDC and IAC and use the values of pi, then you will be getting a number equal to 0.406. So the efficiency is going to be for the half-wave rectifier is going to be 0.406 into 1 divided by 1 plus RF by RL. Okay, and if you neglect that resistance part, it will be 0.406, and if you express that in as a percentage, it will be 40.6. That is the efficiency of the half-wave rectifier. It is, even when what is the efficiency is like how much is the output that we are getting when we give a certain inputs, and all what we have focused so far is that the half-wave rectifier is removing all the positive cycles, or depending on the direction in which you have connected the diode, either it will remove all the positive cycles or it will remove all the negative cycles, but one half of the cycles will be there, but still, that means the maximum that we can expect is 50 percentage, but actually we are not getting 50 percentage, we are getting only 40.6 percentage. So it is interesting to think about like where is this remaining part is going. Something like 9.4% is lost somewhere, right? So that is a question for you to find out the answer. And now we will see the full wave rectifier. Essentially, the full wave rectifiers will not remove any half cycles. Only thing is that it will make all of them rectified. For example, in this case, you have got a positive cycle and a negative cycle in the inputs. But in the outputs, both these cycles are appearing in the positive path. It is not removing, unlike in the case of half wave rectifier, it will maintain all the cycles, but all of them will be maintained to one side, or the current will be flowing only in one direction. So in order to do that, what we can do is, earlier why do we lost one half cycle is because during the negative cycle the diode was reverse biased. So here you can overcome that difficulty if you are using another diode and connect it in the circuit in such a way that one of these diodes will be forward biased during the positive cycle and the other diode will be forward biased during the negative cycle. But the important thing is that both these diodes should be conducting current along the same direction through the load resistance. Okay. So over the years, I have seen some students drawing this circuit. If I don't show them the circuit, and if I ask them to modify the half wave rectifier and draw the circuit of a full wave rectifier, what they are going to do is they are drawing these two diodes like this, and it is correct. But then when they draw the load resistance, they will just connect it in between the two negative two end regions of the diode, right? Like this, over the end, in between the two end regions of the diode, they will just draw the load resistance, which is wrong, because when the diode D1 is forward biased, it will be conducting current, and that current will be flowing downward through the load resistance if it is connected like that. And during the other cycle, the second diode will be conducting, and then in that case the current will be flowing in the upward direction through the load resistance. So essentially we don't have any rectification. So whatever input is there, exactly the same thing will be appearing at the output also. So that is not a successful rectifier. So you have to be careful in the way in which you are going to connect the load resistance, by making sure that the current will flow along the same direction through RL, both during the positive cycle and the negative cycle of the input. Then only we'll be having rectified output. So this is one option. You can connect the resistance between the common point that meets the two end regions of the diodes, and then the other end of the resistance can be connected to the center tap point of the secondary of the transformer. So this kind of rectification is referred to as center tapped full wave rectifier. It is making use of two diodes and the three taps from the secondary will be used. The two ends of the windings and the middle part of the winding will be used in the circuit. So how it is working, the input is here and it is generating some the primary voltage, and then it is stepped down, and during the positive cycle the top of the secondary will be positive and the bottom will be negative, which means only the diode D1 will be forward biased, D2 will be reverse biased, and it will be cut off. So that means D1 will conduct. So the current will start from the top of the secondary. If you want to find out the direction of the current through RL, you have to start from the positive of the source. So in this case, it is the top of the secondary. From there, the current starts. It reaches a diode D1. Then it flows along the direction which is indicated by this arrow in the diode symbol. Then it reaches this junction between the two end regions and the resistance. So at this junction it will have to decide where it should go. So it has got two options. It can either go along RL or it can go to the other diode. But see, the other diode is reverse biased, and therefore it is cut off, so it cannot conduct current. So the current will go, current has got only one option, it can go through RL. So in, and then it will reach the middle of the secondary of the winding. So that will complete one cycle. So during this time the current is flowing from right to left along RL. Then during the negative cycle the polarity will be reversed. The top of the diode will be negative and the bottom will be positive. Okay, so that means the diode D2 will be conducting. Top is negative, so D1 is reverse biased. Bottom is positive, which means D2 is forward biased. So as before, instead of D1, D2 will be conducting now. And to find out the direction of current through RL, you start from the positive of the source. Bottom of the winding is positive, so from there the current will begin to flow, and it flows through diode D2 along the direction marked by the arrow in the diode symbol, and it reaches the junction, and it cannot go through D1 since it is open, so it will go through RL and reach the center tap point and completes the cycle. So in this case also the current is flowing from right to left through RL. So both during the positive cycle and the negative cycle, the output current is flowing along the same direction through RL, and that is how we get rectified outputs. So that is what is shown here. During when you compare the input signal and the output signal during the positive cycle, this is how the output is varying, and during the negative cycle the current is flowing in the same direction as in the case of positive cycle through RL. So we have exactly similar uh, halves at the outputs both during the positive cycle and negative cycle. So that means we haven't eliminated any half cycles when we are making a full wave rectifier. So that is the advantage of using a full wave rectifier over a half wave rectifier. And this type of a circuit is only one option of making a full wave rectifier. We have got one more to learn, and that is the bridge rectifier. One more thing I will tell you before we move to the next topic. I won't do the derivation here. For the case of full wave rectifier, you can proceed as before. In the case of half wave rectifier, you find out the ripple factor, which is root of IRMS square minus IDC square divided by IDC, and IRMS in the case of full wave rectifier is IM divided by root 2, and IDC you can evaluate. The only difference is that you have to integrate between the limit 0 to 2 pi, because during that time you have got the voltage appearing at the output. Or you can even do it because since the variation during 0 to pi and pi to 2 pi, since both are the same, you can even do it like 2 times integral from 0 to pi Im sine omega t. But whatever it be, since it is a sine function, it doesn't matter whether you are doing it from 0 to sorry, you have to do it like 0 2 times integral 0 to pi Im sine omega t. So that means you will be getting IDC equal to 2 Im by pi. Earlier we got it as Im by pi, but here it will be twice as that. It will be 2 Im by pi. So IRMS is equal to Im by root 2 and IDC is equal to 2 Im by pi. So you just can use these values in the equation for ripple factor and efficiency, and find out the ripple factor and efficiency of full wave rectifier. So in this slide I have shown the results of the calculations for IR ripple factor and efficiency of the full wave rectifier. So the equations are as before. For ripple factor, you'll have to make use of the equation root of IRMS square minus ITC square divided by ITC. And for efficiency, it is PTC by PSC, which is the output power divided by input power. But here we will evaluate ITC as I told you just now. It is 2 times 1 by 2 pi into 2 times integral 0 to pi Im sin omega t, and it is just twice as that we evaluated for the case of half wave rectifier. So you will get it to be 2 Im by pi. And by definition, IRMS for a full wave rectifier is Im divided by root 2. So you use these two equations, IT is equal to 2 Im by pi and IRMS is equal to Im by root 2, and use these two values in the equations. First one, a ripple factor equation is the same, and if you evaluate, you will get it to be 0.481. And the efficiency, when you evaluate the output DC power divided by input AC power, then you are going to get it like this. When you assume that RF is very small compared to RL, you'll get it to be twice that in the previous case, and it is 81.2%. This is the second option for constructing a full wave rectifier. You can see that it makes use of 4 diodes and it is called bridge rectifier. The circuit is similar in appearance to the Wien's bridge circuit. So here it makes use of 4 diodes, and when you compare it with the previous one, center tap full wave rectifier, we can see that you are not using the center tap point in the secondary. That means the entire voltage appearing across the secondary of the transformer will be used both during the positive cycle and negative cycle, and that is one advantage of bridge rectifier. The voltage available will be larger, and okay, it makes use of 4 diodes. So in order to explain the working, we will begin to see which are these diodes are conducting during the positive cycle and during the negative cycle. So during the positive cycle, as I told you earlier, top of the secondary will be positive and bottom will be negative. Top of the secondary is positive, so that positive part of the secondary is connected here to the junction between D1 and D3. Okay, so that means the positive of the source is connected to the P region of the D1 and N region of D3. So that means D1 will be forward biased and D3 will be cut off. Similarly, the negative part of the secondary, that is the bottom part of the secondary, is connected to the junction between D2 and D4, which means negative of the source is connected to the negative N region of D2 and P region of D4, which will make D2 forward biased and D4 reverse biased. So you have got 2 diodes, D1 and D2, which are conducting, and D3 and D4 are cut off. So how will the current move? That is shown using this animation. See, it starts from the positive, reaches the junction, goes to D1, RL, D2, and reaches the negative of the secondary. So that makes one complete cycle, and during this cycle the current was flowing from through RL from right to left. See, right to left. So that is the direction of current. Now you can imagine if during the negative half cycle what is going to happen. This animation is for the positive half cycle. If you go to this website instrumentationtools.com, you'll be able to get the animation for the negative half cycle. But you can imagine when during the negative cycle, obviously the other 2 diodes are going to conduct and the bottom of the secondary will become positive. So the current will flow, it will start from the bottom of the secondary, reaches the junction between D2 and D4. D2 will be cut off, so it will move along D4, and at the junction D1 will be cut off, so it will go through RL and reaches the junction between D2 and D3, and at that junction it will go through D3 and it reaches the junction between D3 and D1. D1 will be cut off here, so it will go to the top of the secondary. So in this case also you just draw it in your notebook and find out. Okay, so you will see that during both the half cycles the current is flowing through the load resistance in the same direction. So that is the essence of rectification. Even though the current is flowing in two directions in the case of inputs, when it comes to the outputs, current will be restricted to flow only in one direction. And it is not eliminating any half cycles. It will actually rectify. That means whichever it was more current, for example, in the case of negative cycle, all the negative half cycles will be taken to the positive side, so it will maintain all the voltage. Unlike in the case of a half wave rectifier. So and in this case a bridge rectifier, the efficiency and ripple factor will be the same as that of the center tap rectifier, so we don't do the derivation again here. But you can compare. I suggest you read the textbook and compare the features of center tap and bridge rectifiers. First one is making use of two diodes, second one is making use of four diodes, and the maximum available voltage during positive cycle and negative cycle to the rectifier circuit is only half of the secondary voltage. Okay, and whereas in the case of bridge rectifier the entire secondary voltage is appearing across uh, the rectifier. So that is one advantage. Voltage available will be more. There are some other factors also which we can discuss only after going through some of the parameters of the diodes, like peak inverse voltage. There will be some difference in the peak inverse voltage. These are actually some parameters coming under the rating of the diode. So we will discuss the diode parameters. I actually forgot to tell you all this because we started with defining. Okay, we started with the experiment for finding out knee voltage, AC resistance, DC resistance, etc. But then I thought I discussed the topic of diode parameters, because all these AC resistance, DC resistance, all these are diode parameters. And moreover, in the case of rectifier you are using a symbol like RF. In the case of efficiency, RF is actually the diode resistance, forward resistance. And we okay, in the next class I think I will discuss the diode parameters. Then we will compare the features of center tap rectifier and bridge rectifier. Okay, with that we will wind up the rectifier section. Next class we will do diode parameters and we will solve some problems. Okay, so this is what we are going to do in the next session. We will see diode parameters and compare various features of the rectifiers, and then we will solve some exercises. Okay.